Okay, so let's continue now discussing the cosmological applications of general relativity. And last time we discussed with you that, in principle, yes, if I'm looking at my cosmological solutions, I can have different suitable choices of time. One often used choice of time is physical time, like here, so that you have just dt squared, like physical time, and then the spatial size is growing with a. And another choice of time is conformal time, which means that you redefine a time variable such that the scale factor squared just stands in front of the whole Minkowski metric. Yeah? And of course, using this conformal time sometimes is kind of more convenient because, then all the coordinates here are like on equal footing, so I don't have some big change between time coordinate and spatial coordinates. I mean, in both cases, I can define the Hubble constant, like the logarithmic derivative of a with respect to time. In physical time, that's the usual Hubble constant, as we call it. Like in conformal time, of course, we have something different because the time derivative goes with respect to another time variable. And it's easy to see that this curly h is a multiplied by h, by the usual Hubble constant. And we discussed that I'm looking at the perturbations in the matter sector, like here. And I assume that my matter sector has the shape of the ideal fluid. Yeah? I mean, at large scales, usually it's kind of good enough approximation. And if you have, let's say, a scalar field, then scalar field always has this type of energy momentum tensor, at least as long as the gradient is time-like. Because like the gradient of the scalar field would reproduce you the for velocity. If you go for electromagnetic field, then yes, the energy momentum tensor is not of that shape. So if I really would like to discuss like B mode of polarization in CMB, I would need to go beyond the ideal field approximation. So, but in principle, yes, it's just about changing the right-hand side of my equations. So that's the simplest case when I assume that my equations are like for ideal fluid, right? And already here I separate the velocity of my ideal fluid into the divergenceless part, like rotational motion, and the gradient, which is kind of potential flow. And the reason again is because I'm studying perturbations around spatially homogeneous and isotropic solution. So if I have some kind of small perturbation, like some divergenceless vector, maybe multiplied by some function of time, plus maybe some another function of time, and then gradient of some another scalar function equal to 0. I take divergence. This guy by definition gives me 0, and here I have then like the Laplacian is equal to 0. And since I'm looking at small perturbations, I don't solve it like I don't know 1 over r or something. I just say, okay, if the Laplacian is equal to 0, I just take u equal to 0. Like separately for the scalar case, and then the vectorial part also has to be 0 separately from that. So yes, that's the idea of separation of scalar vector and tensor perturbations of linear order around my symmetric solution. And then after that, I go for parameterizing my perturbations of the metric in terms of 4 scalars, f, phi, f, s, psi, 4 scalars, 2 vectors. Like these mixed components also might have divergenceless part here, this vector v, and divergenceless part here, vector c. That's already like 8 components. And then I also have transverse traces part here, by which I mean that I take trace, it goes to 0, and if I take any of possible 3 divergences, it also gives me 0. So transverse traces guy here. That's why I put here like TT, transverse traces. And that's actually the gravity. And altogether I have like 4 scalars, 2 vectors, each of which has 2 independent components. So already 8, plus this transverse traces guide, which also has 2 independent components, 2 usual polarizations of a graviton, which means like 10 independent components here. And then after that I can remember that I also have diffeomorphism and variance in general relativity. I can change coordinates as I wish. Of course it changes somehow all these components here. And from the point of view of SO3 rotations, this guy has two scalars, like an z time component, and the gradient part of this spatial components, and one vector, which means like the divergence is part of the spatial components, which means that by doing gauge choice, I can kill two scalars and one vector. So the choice which theoreticians very often like to do is to kill f and s and to kill the guy c. Why we often like that? Because in principle you can also try to find out the gauge invariant variables. And you will find out that in this gauge, the gauge invariant variables are basically equal to v phi psi. Because in principle those Bardeen variables would be something like v minus c dot and then phi psi plus some expressions in terms of like f minus s dot or something like that. So in principle if I kill these guys, my gauge invariant variables will just coincide with the phi psi and v. So basically from now on I kill f, there is no this term, I kill s, no this term, and I kill c. That's my gauge choice. And after that I have to substitute this parameterization of the metric fluctuations into the Einstein tensor. And as last time I was explaining, it can be done different ways. You can either just perturb the Einstein tensor directly around the background solution like here, or in principle you can perturb the Minkowski metric here, and after that do conformal transformation with the a squared. Both ways are not very simple, but you can do that. And the final result I wrote here. So that's what you get for the components of the Einstein tensor. For example, let's have a look at this zero time-time component. In the time-time component, yes, this guy is the background value of the Friedmann equation. And these guys are perturbations. If it was around Minkowski, then no Hubble constant. So you just get the Laplacian of psi, the usual Laplacian of the Newtonian potential and gravity. And actually that gives you the idea that this potential is not dynamic. It's restricted to the energy density in the right-hand side of the Einstein equation, right? That's actually very good news that psi is non-dynamical, because otherwise it would have been lost. If you look at the spatial components, you have the psi double dot, the acceleration of psi, and actually it goes with the opposite side to the acceleration of the gravitational waves. Actually, if you have a look at the quadratic action around Minkowski, you can find out that psi has the wrong sign kinetic. It has like ghost energy. And what saves GR is that actually psi is constrained. So it doesn't matter what it has there, it's anyway constrained. And that's actually related to what you have seen yesterday from Maria Costa lectures. Because you could see like the kinetic term going like in terms of extrinsic curvatures. Like that. And that's of course not like the sign definite expression. For 6 variables, Kij, you get like 5 plus and 1 minus. This kind of supermetric has signature of plus, 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 minus. So this minus is what gives me the wrong sign of the acceleration here. And again, I'm safe because I have the constraints, which remove this dynamical mode. On the other hand, that gives you some idea why modifying gravity is so difficult. If you add some kind of mass term to the general relativity, you break the Fermat-Hussman invariance, you remove the constraints, and you get the goals back to life. So that's one of the reasons why it's so difficult to modify Java without destroying everything. Okay, so anyway, finally I have these expressions here. Of course, like time-time components, they have only scalar modes. The mixed component, it has both vector mode and scalar perturbations. And the spatial components, they have everything. Yeah? They have the gravitational waves here, the tensor perturbations. They have the vector perturbations here. And all the rest is about scalar perturbations. Okay? And of course, this guy again is just background thing from the Friedmann equations. Okay? So let's just discuss a bit about what we can see here. That's the result which you, I mean, of course you could also find that using computer if you're lazy for doing calculations yourself. Even though it's not like a very big calculation, you can do it in one evening. Okay. So, let's first discuss about the gravitational waves. I just removed all my parameterizations here. Now, the important thing is that we see the results. Okay, I'm stupid, I removed also the energy momentum tensor. So, the gravitational waves. I have just removed the energy momentum tensor for the ideal fluid, but you could see that there are no tensorial perturbations, only scalar perturbations, basically like variation of energy density and variation of pressure, and the potential flow, and there is also one vectorial perturbation, which is like the divergence is part of the flow, like some rotational motion. So, and there is no tensorial perturbations. That's because I restrict myself to the ideal fluid. Yeah. In principle, yes, for electromagnetic perturbations, I also have something there, and they can have some interaction with the gravitational waves. But like in this approximation, the gravitational waves have nothing in the right-hand side of the equations. So basically, I get the equations for the gravitational waves, like here. And that's, I remind you, that's written in conformal time, because if I go for physical time, I will also change the coefficients here. That's in conformal time. And the basic idea now is like following. You see there is no term, just h. It's either time derivatives of h or Laplacian here. And now you can imagine that the very different things are for short wavelength perturbations and for long wavelength perturbations. Like if my wavelength is very short, then basically this term is not important. I can forget about that and I have just the usual wave equation, like for usual gravitational waves in Minkowski spacetime. I mean, if you can play a bit with that, you cannot actually convince yourself that the important things is like physical wavelengths. By physical, I mean not with respect to coordinates, but like physical length indeed, multiplied by the scale factor, and the Hubble length, which is basically Hubble constant -1, Hubble constant in the physical time, like Hubble time or Hubble length, because I put the light velocity to 0 to 1. Yeah. So basically, if your wavelength is much less than this guy, your wave doesn't feel the curvature of space-time. It basically lives in Minkowski space-time, and you have the usual wave equation for gravitational waves. If vice versa, you go for very long wavelength, and basically you can neglect the Laplacian here. Laplacian is almost 0, and then basically you have like h double dot plus 2h dot equals 0. How can you solve it? One thing is like h dot is 0, which means that h is constant. That's kind of obvious solution. Another idea is, and another possible solution is that h dot over h is equal to minus 2a dot over a, which means that h dot decays like a 1 over a squared. That's in conformal time. In physical time, of course, you know, there is difference. In physical time, it would be like 1 over a cube. So like, for example, if you have some accelerated expansion, then of course h decays very fast. The most decelerated expansion, which is like in radiation-dominated universe, a goes like square root of t, so it goes like 1 over t to 3 half, which means that h also decays. Decays like 1 over square root of t, like that. So basically what we get here is that if you go for small wavelength, then you have just the usual wave equation, because you cannot distinguish from the Minkowski space-time. If you go to large wavelength, you have two modes. One mode decays, almost always, like you should invent something very exotic so that it doesn't decay. In all like real cosmology it decays. And one mode stays constant. Okay? So that's the idea. Okay, basically, since I started talking about this short and long wavelength, let me discuss what kind of ideas here. Like physical wavelength, it goes proportional to the scale factor. Yes, everything just expands like a scale factor. And if I assume that my universe expands decelerated, like with the power law with p less than 1, like it's 1/2 for radiation domination, 2/3 for matter domination, the usual cosmologies. So basically my wavelength grows like t to power p, like that. At the same time, what is my h? It's kind of, I take time derivative here, I get like p multiplied by t to power p minus 1 over tp. So basically that's p over t. And that means that the Hubble scale grows like t. Basically, this Hubble scale is mostly like the causally connected part of the universe. That's how much a photon, for example, could have traveled before that. So basically, this curvature scale grows faster than the wavelength, which means that
it's constantly connected within the Hubble time.
Yes.
Yeah.
So which means that in a decelerated universe, basically the wavelength, which used to be very large compared to the scales, which had like the wavelength larger than you could see, this wavelength, they become shorter than this scale. So basically the wavelength, which used to be very long for us, with time it becomes shorter and shorter, and we can see new and new perturbations. Okay, I'm talking about us in the scales of billions of years. So somehow several billion years more, and then we can see new wavelengths.
Yeah, just like this is within the Hubble expansion, different from the particle horizon in general.
Yes,
In
yes,
general.
yes. Okay, as long as I just go for that, then particle horizon and Hubble scale is mostly the same. Just
Yeah,
like
here it's
one.
the same.
Yeah. Here is not the same, yeah. Which can be seen just from here. Like, because Hubble time is like some order unity coefficient multiplied by t, that's basically the same as the distance that would have been traveled by light. So as long as I restrict myself to this kind of classical cosmology, it means that particle horizon, like causal horizon, is basically the same as the curvature scale here. So that's the final idea. But what I was going to say is that yes, indeed, like in this decelerated expansion, we have some waves which are very long, we cannot see them, but if we wait for several billion years more, we can see them. They're already like inside our horizon. Which is kind of, on one hand, good, because we don't need to know much physics to describe them, because they're just very long, I don't feel what happens here, so it's just some kind of constant mode there, nothing special. On the other hand, of course, if I take it like that, I don't know what kind of initial conditions would be natural to take for them, because they're just outside any causal horizon. Okay, so that's about the gravitational waves. Next thing here is the vector perturbation. Vector perturbation, first of all, I can find it here in the mixed components. And in the mixed components, vector perturbation will be related to the rotational flow of matter by the mixed components of functional equations. Just like, again, some kind of constraint. Again, the vectorial mode is not dynamical. It gets constrained to this velocity here. And another contribution goes here in the spatial components. Yeah? And in spatial components, my ideal fluid does not give any contribution, because in spatial components, this contribution will go like that, and that's second order perturbations. So basically, in linear theory, this part should be equal to 0. And what do I see from that? What do I see from that is the following. Okay, let me just go very easy. I remove the derivatives, and I basically have something like that. Minus 1/2 v dot minus h3 is equal to 0. Yeah? So what does it mean? It means that y dot over v dot over v is equal to minus 2a dot over a, which means that v decays like 1 over a squared. So that's the basic result why in cosmology textbooks you usually don't see any discussion of vector perturbations. They decay. They just decay. I mean, at least like at the level of the metric perturbations, vector perturbations decay. You can also calculate it in terms of the vector perturbations in the velocity, and it mostly also decays. Only like for radiation domination, the physical velocity stays constant more or less. But otherwise, the vector perturbations, they always decay. That's not like a big surprise, because like, you still have kind of rotation invariant space-time, and you study perturbations around that. And this rotation invariant space-time, it expands. And if you are doing some kind of skating, you can imagine that if you skate like on your skates like going around, and then you just stretch your arms, you slow down because of momentum conservation and the momentum. So that's basically what happens here. So there is no surprise whatsoever. And in principle, yes, mostly for gravitational perturbations in usual cosmology, vector perturbations are not of any interest. Unless you do something crazy. You introduce some vector fields for inflation, like I did at some point, or something like that. On the other hand, it's also another problem, because basically what you can see like from this kind of decay of vector perturbations is that basically your theory does not give you any kind of natural dynamic mechanism for producing magnetic fields, for example. And that's another problem, like what is the origin of the primordial magnetic fields in galaxies. So that's another story. And then what we are left with is the now scalar perturbations. Scalar perturbations, okay, in the mixed components, basically the scalar perturbations would relate my potentials would relate to this potential flow of my fluid. So basically I will get like potential from here, given in terms of psi dot plus h phi. That's all right. And then let's look at the spatial components. The spatial components, they have the diagonal part, and they have also off-diagonal part here, which basically, and actually the perturbations of the energy momentum tensor, they are only diagonal. Like it was p plus delta p delta ij. Which means that for I not equal to j, the second derivative of phi minus psi must be equal to 0 by equations of linear perturbations. And as I told previously, I'm doing perturbation theory, just some small perturbations. So if my second derivative is 0, I just solve that like phi equal to psi. That's it. I mean, of course, it could have been some linear function on coordinates, but it's not small. So I solved like phi equal to psi, and actually that should be very familiar for you maybe tomorrow when Adam introduces black holes. You can look at Schwarzschild's solution, Taylor expanded around Minkowski, then you can see that like phi is equal to psi. The deviations from unity in dt squared and dr squared. So basically that's the result. Then it means that this, and then already before that I discussed that psi is constrained. Now I see that phi is also constrained, phi is equal to psi, which means that gravity does have only 2 degrees of freedom. Yeah, it has 2 degrees of freedom of 2 polarizations of the gravity. All the scalar and vector perturbations are constrained. Like, there were like eight variables. 4 of them are just pure gauge. 4 other are physical, but they are constrained. They do not propagate in time independently. Okay, now let's have a look at the final part of the scalar perturbations. Now you see, what I still have here is like, here in temporal components I have these perturbations, and that will be proportional to perturbation of the energy density by Einstein equations, temporal components of the Einstein equations. And I also have, okay, phi is equal to psi, so this guy just disappears, but otherwise I have this thing here. And by spatial part of the Einstein equations, it should be proportional to variation of the pressure. Okay, So, and somehow, yes, here I have like Laplacian, here I have second time derivative. I mean, it would not be dynamical by itself, but since it couples to my ideal fluid, then basically I do get some kind of dynamical equation if I relate the perturbation of the density to the perturbation of the pressure. And then I get this dynamical equation, which is basically some acoustic wave in my fluid. Okay? Yeah, and maybe like one more comment. Why I did not have non-diagonal perturbations in the spatial part is because the fluid is ideal and has the pressure isotropic. So I do need to have some kind of anisotropic pressure here if I want to have psi not equal to phi. So basically then the basic idea is that I need to have some kind of equation of state for my ideal fluid, and after that I get the equation of motion for the perturbation. So usually we say, okay, let's say that, okay, let me now just follow my notes because otherwise I can have mistakes in some simple things. Yeah. Okay, let's say that the perturbation of the pressure is some coefficient multiplied by perturbation of energy density. Yeah, the coefficient is of course the sound speed squared, not by chance, just because it indeed would be a sound speed squared if I do it like in the usual Minkowski space-time. And finally, okay, and everywhere I can put like phi instead of psi because phi is equal to psi. So basically I take this part, it's given by variation of pressure. I take this part, it's given by variation of energy density, and I have this equation, and I get the equation for phi. So what I basically get is the following. Okay, again I have some terms with second time derivative and the first time derivative, and then I get some term which doesn't have derivatives. Phi. And then I also have a Laplacian phi. So that's the result. On one hand, yes, you can clearly see that that's indeed a sound speed squared, because if I'm in Minkowski, h is equal to 0, and I get the usual wave equation. On the other hand, what is different from the gravitational waves case is that I do have this term, which has non-zero coefficient in front of phi. Actually, if my equation of state is just constant, like if I have p equal some w rho, that's what is called equation of state parameter. And of course my w is just the sound speed squared from here. And then in this case I can put w here, and you can check that this coefficient is actually 0 by Friedmann equations, just by Friedmann equations. And in this sense, like, you know, as long as I have some particular constant value of w, like radiation dominated universe, w equal to 1/3, or matter dominated, like w equal to 0, the Newtonian potential phi for large wavelength will have like one constant mode and one decaying mode, again, like for gravitational waves. If w changes, then the constant mode is not constant any longer, but actually that's just because I chose not very convenient variable. In principle, you can prove, I have no time to discuss geometry behind that, you can prove that if you go for another variable, like psi minus delta rho over 3 rho plus e, that variable indeed will have, you know, a constant mode for large wavelength. And basically, like in usual cosmology, the most important change is when we go from radiation domination to matter domination. And then you can check that actually the usual Newtonian potential will just get multiplied like by 9/10 of the initial one. So you will have some change, but anyway, again, like for gravitational waves, you know, for short wavelength, you have some usual Newtonian physics, like usual acoustic wave, usual wave equation. For large wavelength, you basically have one decaying mode and one mode which kind of stays constant, as long as its wavelength is much larger than the Hubble scale. Okay? So that's the basic stuff here. And again, the problem is that we do not basically know how to find the initial conditions for these perturbations. Okay, so how much time do I have? Let me maybe discuss a little bit of physics behind cosmology. I guess for now it's enough of these huge formulas. I showed like the most important things, and then after that you can just use that and calculate whatever you want. So let me first discuss with you what kind of initial plasma, primordial plasma I have before recombination. Basically, I mean, these Newtonian potentials, of course, they are also related to this, energy density perturbations, which basically means that they are related to the fluctuations of the temperature in primordial plasma. And that's basically what we see now in CMB, in cosmic microwave background. What kind of temperature perturbations were there. I mean, in principle, that's this kind of Sachs-Wolf effect that, basically the temperature perturbation we receive is like initial temperature perturbation there, plus this Newtonian potential, because if it was like some kind of potential hill, the photon travels to us, and then going down the hill acquires some energy, and vice versa. If it was some potential well, it has to climb up and then lose some energy. And then I already erased everything, but yes, you can in principle relate the variations of temperature, temperature itself. You can relate to the equations, and you can even see that what we see is basically some kind of inverse image. The regions which were the most hot, they were like the potential wells, and basically from the most hot regions you get like the coldest spots in CMB and vice versa. But otherwise, yes, that's the Sachs-Wolf effect. On top of that, you have also some corrections like Doppler effect from the velocities there. You also have what they call integrated Sachs-Wolf effect, because the photons later propagate in a varying potential. The potential varies because of change in the equation of state. Basically, there is early effect because of going from radiation to matter, and then late effect because of dark energy coming into play. Okay, and things like that. Then you can also ask yourself what kind of sound speed you have around the combination. And for that, actually, you can also play some simple games, like basically what we are talking about adiabatic mode. And how you can find an adiabatic mode, the entropy goes like T cubed.
Maybe Alexey should give a little background to what your combination with CMB, because they probably don't know what.
Okay.
Do you know what the cosmic microwave background is and the combination of that? You guys know? Who knows? You know? So maybe just very quickly.
Okay. So maybe let me first derive the sound speed, and then I discuss
What is your combination?
Yeah. Anyway, sound speed is sound speed. It was there irrespective of anything else. So basically, the entropy goes like proportional to T cubed, and because it expands, I have to keep track of the same volume, which goes like larger and larger. So it should be like related like to, let's say, density of baryons. Like for one baryon, you have different volume, and finally you calculate the entropy there in this volume. So variation of this guy should be zero. The energy density of photons is proportional to T to the 4, right? The energy density of the baryons is just the mass which goes like, the volume grows like A cubed, yeah? Which means that it goes like 1 over T cubed. So that basically goes like do I need that? No, I don't need it now. Anyway, so for baryons it would be cubed. For photons it's power 4, because also every wavelength changes. Yeah. Then here I basically have that should be equal to 0. My mode is adiabatic. Then it means that it's a variation of like rho gamma to the power 3/4 over rho baryons. Yeah, which means finally that 3/4 delta rho gamma over rho gamma is delta rho baryon over rho baryon. That's the adiabatic perturbation there. And then finally I just see that the sound speed squared, which is like variation of the pressure or variation of density, how it goes. Variation of the pressure is 1/3 delta rho gamma, right? And variation of density is variation of gamma plus variation of baryons. And then let me just divide by rho gamma. I have like 1/3, and here 1 plus delta rho gamma, delta rho baryon over delta rho gamma. And I look at here, and so delta rho baryon to delta rho gamma is like 3/4 rho baryon to rho gamma. And finally I get the result. Yeah. So basically, if there were no baryons, yes, the sound speed like in photons is like 1/√3, and here is some kind of correction. Okay, so now yes, I have to discuss about what is CMD. So we did have this kind of primordial plasma, basically photons, baryons, okay, dark matter, neutrinos, everything. And as long as you have high temperature, what happens is that you don't have atoms. Yes, you have basically, let's think only about the hydrogen. You have protons and electrons. They might be combined to have a hydrogen atom, but then the temperature is huge, so it gets hit by some photon and it gets again to separate protons and electrons. So you have a plasma. And of course also the photons are not precisely free because you have lots of charged particles around. So that's basically some kind of plasma there, which speed of sound we could just calculate here. And then the temperature goes down. Actually it should go down quite a lot so that you can get the neutral hydrogen. Why? I mean, because if you think about hydrogen atom, like how much it was, like 13 electron volts or something like that. So basically it corresponds to like, I don't know, 150,000 Kelvin. But anyway, like in the actual universe, the combination occurred at the temperatures around 3,000. Or if you want like redshift, like something like 1100. Yep. So why is that? I mean, because as you know, we don't have so many baryons somehow. Yeah. In a sense, it's not surprising because baryons and antibaryons should have annihilated itself, but somehow we still have too much of that. But anyway, like the number of baryons is like billion times less than the number of photons. So the baryons are kind of very rare. That's why it means like for every baryon, every hydrogen atom here, they have very many photons around. That's why even like the high frequency tail of the Planck distribution plays a role. And still, I mean, finally you can go to the combination only like at temperatures around 3,000 Kelvin. Actually, another funny point here is that this is an example of a process which doesn't go in equilibrium. I mean, if you want to study like some kind of plasma around let's say star, and you want to find the ionization fraction there, you can derive a funny thing which is called Saka equation. It's not very difficult, but I don't have time. And you can find out like which is the equilibrium ionization fraction there according to the temperature. But here in the universe it doesn't go like that because if you have finally if you have from some higher level if you go to 1s you need some photon, high energy photon, And you know, if it's some kind of plasma around the star, the photon finally just leaves and goes away. It cannot just leave the universe. It still stays there. And basically, yes, it ionizes another atom. So that's why ionization cannot go like in the usual equilibrium way, like Saka equation would predict for you. And basically, to predict the outcome, you need to use some kind of kinetics theory. And final point is that very important in processes which are kind of very much forbidden, like 2s to 1s, which goes only via like 2 photon emission. And that's why, because you get here like 2 photons, they have not enough energy, and then the atoms can stay in your state. But finally, anyway, like at this temperatures of about like 3,000 plus minus, let's say 300 Kelvin, you finally go from the fully ionized plasma to almost fully neutral matter. You have
You can get an order of magnitude from just log 10
yeah. I mean, even like if you want to find
I have also in fact the log of
yes. I mean the temperature, yes, you can find like that. Like even initial stages of recombination, yes, you can find from Saka equation. it doesn't work. Yes, it doesn't work only once and when you get like lots of photons around, so that then it stops to be efficient. So finally, yes, you have this recombination. And what's after that? After that, you have some neutral matter, neutral atoms, and you still have photons around. And nowadays, photons are almost free, yeah, because they don't have charged particles around. Okay, a bit later there will be a reionization epoch from the first stars, but anyway. So basically, after that, the photons can travel more or less freely through the universe, with basically optic depth like less than 10%. So which means basically that most of the photons which were there after recombination, most of them traveled all the way to our eyes without any kind of scattering. So basically it means that the photons in the universe, they were just living freely, and what we see kind of a good enough photo of the status before recombination. So that's what we call cosmic microwave background. Those photons which were there. Of course, yes, the universe still expanded, so the temperature of these photons were going down. So nowadays it's like 2.7 Kelvin, something like that. But still, finally we have this recombination. Okay, to be very precise, since the recombination was not very fast, it took some time. The high frequency modes are kind of damped there, also because of this, not instantly taking the photo. But otherwise, yes, that's what we get. We basically get what was there, kind of photo of the perturbations in the early universe. I mean, yeah, in principle, yes, if we are talking about physics, then on one hand, you can try to see that in principle, yes, very many things were in equilibrium. You can check that, of course, the universe expansion for photons, it makes the momentum going like 1 over A, which means basically the temperature is going 1 over A. If you had just some kind of Maxwell gas of non-relativistic particles, then it would be like P squared over 2m, the energy. That would give temperature going like 1 over A squared. So in a sense, the universe expansion would contribute to going away from the equilibrium. But anyway, the baryons are very, very deep. So basically, all the temperature goes like for the photons. And there are also some kind of funny points when you have this unequilibrium processes, like for cosmic microwave background. Yeah? So, okay. If I started talking about cosmic microwave background, let me maybe talk about it a bit more. Like you can also go, back in time. And once you go back in time, okay, one more thing. Let me mention one more thing before going back in time. If you want to compare the Hubble time like that, and the basic time, like for example, for change in energy of photons, you can like go for usual kinetic theory. Yes, you can try to estimate the rate of interactions here, which would go like concentration of electrons multiplied by the Thomson scattering section, and then also you can find out that each scattering changes the energy of the photon very little, because yes, you have the momentum given basically by the temperature, but more or less this kind of momentum you give to the electron, it means that the electron acquires energy like p squared over 2 electron mass, and it changes the energy of the photon very little. It changes mostly the direction of propagation, but not the energy. And then you can find out that the rate of the change of energy in these things goes like t to 5. Unlike the Hubble time, which would go maybe like square. So basically it means that at high temperatures, you have very well preserved equilibrium, like the usual statistical physics. If you change the external conditions slow compared to internal processes, you can still stay in equilibrium. So then you can check actually that if you had, for example, some crazy ideas, like you had unstable dark matter decaying at around recombination, you might have spoiled the Planck spectrum of the CMB. So that's why actually nowadays people are also trying to study the spectral distortions of CMB. Because if you find some distortion, there might be some trace of some processes not much before recombination. Because just before recombination, this equilibrium was not already was not very ideal.
Well, there's many other things.
Yes.
Primordial black holes.
Yes. You can have lots of ideas why.
Lots of things. Yeah. And power spectrum. Like,
yes. But in principle, yes, if you try to estimate how fast we can change the energy of photons, and compared to the Hubble times, it will give you that basically after like maybe 10 to the 5 Kelvin, it won't be already like very efficient. And in the processes changing the number of photons, they go out of equilibrium even before. So if you have some crazy ideas just before recombination, then yes, you might spoil the observational data.
Yeah, I'm just saying that it's also a test ground for many other things.
Sure.
So
Absolutely.
So this is how you can test things in
Yes.
universe particle physics
Yes.
and other
Yes.
ideas.
Yes.
Many other ideas.
Absolutely. So that's the point. Yeah. And if you go back in time, you have another funny story, which is called nuclear synthesis. And for nuclear synthesis, it's again a process which is not in equilibrium. Because if it was in equilibrium, what kind of nuclei would you first get? That would be helium-4. Because that's the biggest mass defect, so the most stable nucleus. And so that's the thing which would have been first there. But how can you get that? You have protons, you have neutrons, and yes, the first thing you can get is like hydrogen 2, right? And that's not so stable at all. And basically, since the plasma was not very dense, you cannot go around. You must go through this deuterium stage. And that's why, again, it's not an equilibrium process. To really predict nuclear synthesis, you have to also go to some physical kinetics. That's another story. And actually, it's a very interesting story because how much of the helium you can produce depends on how many neutrons you have. And the neutrons are, of course, not stable. They decay. Like proton, electron, antineutrino, right? And I mean, at high enough temperatures, you also have like back reactions. Like proton meets electron, and they produce neutron and neutrino. So the question is, when the temperature goes down enough so that you stop producing neutron back, when all these weak interaction reactions, they stop being efficient enough.
But then again, the first order, it's equilibrium density of load of neutrons to protons plus the neutron decay.
Yes. So basically, initially you have equilibrium density, and that goes all the way up like to 10 billion Kelvin, like about 1 megaelectron volt. That's about like 1 second of the age of the universe. And after that, the neutron starts decaying. And it decays all the way until, this process of nucleosynthesis goes efficient enough. That's around 70,000 like 70 kiloelectron volts, more or less. And then how much helium you produce depends on how many neutrons were there left. And that very much depends on what kind of, for example, light species of particles you have. Because you have different amount of light particles there, and you have different expansion rate of the universe, and it changes time from 1 mega-electron volt to this 70 kiloelectron volt.
You can make constraints on how many neutrinos there are actually.
Yes.
How many species.
Yeah, precisely. So that's also like another interesting point here. Basically, you have some kind of nuclear physics, and you can use that for cosmology. That's very interesting too. And then you go backwards in time, you find some phase transitions, like for example, electroweak phase transition and things like that. And you can also study things like if you can get some quark nuggets or whatever strange things. And actually, there is also like one big problem here is like, still, why do we exist? Because yes, in principle, even if the universe was symmetric, baryon, anti-baryon symmetric, it would not be able to annihilate fully because at some point it's too huge, and then they cannot meet each other happily and die because. But if you estimate that, you would find out that if it was like totally symmetric, you would get baryons like even 1 billion times less than you have. So still, the amount of baryons we do have is kind of strange. And
that's assuming a weak and what kind of cross-section is that?
I just the usual standard model. If you assume that just a standard model is there, you just have the usual annihilation cross sections, and basically the remaining density appears when these cross sections are not efficient enough because of the universe expansion, and then you get like
when you get a freeze out of the variance.
Yes. But this freeze out is like billion times less than what we have. So, and the conditions which Sakharov found for producing baryons were like key conditions, like C and CP violation. Okay, C violation is what is there in weak interactions just because of this chirality there in the model. CP is actually also there, and that's something which uses 3 generations. Because as was mentioned, these generations of fermions are not just separate from each other. There is this mix. And if it was only 2 generations, then they would give you only one angle. If you look at which kind of phases are not there, just change of value. Once you have 3 generations, you do have like 3 other angles and 1 phase on top of that. And the phase allows you to have CP violations, which is of course observed in experiments, though it's not very big. Then you also need baryon number violation.
So the CP violation of the standard model is not enough.
It's not enough, but there are three conditions: C and CP, baryon number violation, and also like non-equilibrium, like going away from equilibrium. In principle, yes, you can go like for example for phase transitions, and then it's not precisely in equilibrium, even though like the usual phase transition of standard model is very smooth. It's like second order, if not like smooth crossover, so it doesn't help you. C and CP, okay, it's like maybe the easiest part. Then you also need the baryon number violation. And baryon number violation, strictly speaking, it is there, but only non-perturbative in standard model. Like the story of this different vacuum, instantons and stuff like that. If you believe in non-perturbative quantum field theory, then standard model does have some baryon number violation, but at 0 temperature it's like 10 to minus 160 or something like that. So, but yes, at high temperatures, high energies, you might have also try to go like instead of tunneling to go like around the potential with spirons like ready to fall. That should be like temperatures at about maybe 10 tera-electron volts or higher. And the problem is that yes, baryon violation is only this kind of very small non-perturbative stuff. The non-equilibrium is not very much there, so you are in trouble. And then, yes, you might go like for some supersymmetric extensions to change the nature of phase transition. Maybe let me just mention one thing before we stop. Like what is now kind of, that's about baryons. Why about baryons? Of course, we also can talk about leptons. Leptons are also like conserved. I mean, what is not conserved by neutrino oscillations is like separate electron lepton, muon lepton numbers, and tau lepton numbers. The total number of leptons is the same status like bariums here. It's conserved, but it can be changed non-perturbatively. What is always there is b minus L. That's why some people are trying to hedge it. But why don't we talk about lepton numbers? Just because it's very hard to estimate. We still must have the neutrinos around us, the background of neutrinos, like photons. Neutrinos would be even a bit colder, because when the electrons were annihilating, neutrinos already decoupled, throws out. So that's why the neutrinos should be like about 2 Kelvin. And apparently, from experimental point of view, it's almost impossible to find this neutrino background of 2 Kelvin around us to check, to observe that. And one of the ideas nowadays, like most popular ones maybe, is that you can produce first leptons, and then the standard model would, shift part of L to B. Because if the spirals are efficient enough, as long as you have the thermal equilibrium, there is some kind of particular ratio of L to B relation. So you can do that, and in principle, if you go like, again, the problem of standard model, we know that the neutrino does have mass because of the oscillations. And if you want to produce mass in the standard model, yes, you can give the Dirac mass, like left component, right component, left component, right component. But then you have new right components, which is not very good, especially also for cosmology, like some new relativistic species. And you can give them Majorana mass. Majorana mass, it gives you like, the mass just for the right kind of stuff, and still 0 here. And the guy here is really like lepton number violating, because the neutrino becomes just its own antiparticle. It's absolutely neutral. So if you have this kind of stuff, for example, at grand unified scale, in some grand unified theories, you can produce big lepton numbers. And if you look at this mass matrix, actually, you can find the eigenvalues. I'm lazy now to find them. But if M capital is much larger, then one eigenvalue is almost like M, and another eigenvalue, because the determinant is minus M squared, another one is like minus M squared over M big. And on top of just having some heavy particle to produce lepton numbers, for free, you have the explanation why the neutrino masses are so small. You have this kind of thing here. So that's one of the types of seesaw mechanism.
But you have to interpret it in terms of some microscopic scale M.
You have to, yeah. Yeah, but that's one of the most popular ideas now for baryon number production. You first produce leptons with this kind of things, and then it goes to the baryon also. So yeah.
This is baryogenesis in terms of literature.
Yes, precisely. Well, that's it. Okay, so now we have apparently to stop for lunch. So I guess finally, yes, it was not intended, but finally I gave some overview of some general picture of cosmology. So I hope it shows that it's very interesting, because you have lots of different fields of physics which you can apply and then check using cosmology. And tomorrow I'm going to talk about why people were not happy about that. What are the problems of standard big bucket cosmology, which led them, to invention of what's called cosmic inflation around the time I was born.
Okay, great. Thanks a lot. Very nice stuff. Questions? Hayvani? I think hayvani intisal. Vegeting. Hayvani? Oh, awesome. I think that. We have to be back at what?
20 minutes?
12:30.